Okay? Okay, we're starting here with a drone's eye view of what we call the antimatter factory here at CERN, the antiproton decelerator and the Elena rings that provide antiprotons to low-energy antimatter experiments. Okay, so now we're zooming in on the alpha experiment, which is working with the antihydrogen atom. We have to make antihydrogen atoms by synthesizing it from their components, which are positrons. We get positrons from a radioactive source, retrap some of the positrons, and then we're going to shoot them up into the vertical alpha G machine, which is where we're going to actually do the gravity experiment. So we trap some positrons, and they're just going to wait there for some antiprotons, which come from the AD and the Elena rings, pass through the beamline, turn the vertical corner up into alpha G, where they're again dynamically recaptured. So now, after some manipulations, we have a cloud of antiprotons and a cloud of positrons, and we want to make antihydrogen inside of what we call the atom trap, which is a magnetic bottle that will hold on to the neutral antihydrogen atoms. Antihydrogen atoms are formed by two positrons which collide in the field of the antiproton. One of the positrons gets captured, and you have a neutral antihydrogen atom, which is trapped because it's a little bit magnetic. Now, most of those that we make are actually moving too fast to be trapped. So they escape and annihilate, that's what you see there. But a few of them will be trapped each time. Crucially, we can repeat this process any number of times and accumulate antihydrogen atoms by putting in more antiprotons, positrons, mixing them together in the same volume, and then holding on to the newly created atom. In this experiment, we did this about 50 times for each point that we measured. Again, most of them, when they're formed by mixing antiprotons and positrons, are not captured. So now the idea is to release them slowly. We want to release them to see what gravity does to them. So as we slowly release the barriers on the top and the bottom, some of the atoms will go out the bottom, some of them will go out the top, and they'll annihilate so we can detect them, and we can count how many went each way. Now, for normal matter, hydrogen in this machine, 80% of the atoms should go out the bottom under the conditions of the experiment. The purpose of the current experiment was to test that behavior for antihydrogen, and that's what we've done. In fact, we find that the behavior of antihydrogen is consistent with the behavior of normal matter in the same conditions. So the difficult thing about this experiment is that you need neutral antimatter in order to observe an effect of gravity. Gravity is by far the weakest of the four known forces, so it's impossible to observe a gravitational effect if you have a charged particle. But even though we've known about antimatter since the 1920s, this is actually the very first time we've been able to make direct measurement of the gravitational effect on antimatter.
Yeah, some of that was certainly stupid. But still, fly, mostly stupid.